So let's go back to social media with Jeff and see what other questions are waiting for us.
All right. Well, we have an interesting question. Actually, this question is kind of a universal question, and I don't know. When I was a little kid, I liked to watch Back to the Future all the time, and there's like the lightning went into the DeLorean and went into time. So, how much electricity exactly is in a bolt of lightning?
1.21 gigawatts.
Exactly.
Easy.
That's what Doc
Next question.
Yeah. Well, Back to the Future reference, great Back to the Future reference. Also, gigawatts is how we would pronounce it. But that movie was from the 90s, so it's all good. Really, such a great movie, though. Yeah, so answering the question, how much electricity is in a bolt of lightning, is actually a little bit tricky, as you can imagine. It's not like every bolt of lightning is exactly the same. Also, there's different ways to measure electricity. Also, I could just give you a number. Like I could tell you that lightning bolts have between 5 and 200 kilovolts of power, and that's ultimately meaningless to us. So what I'm going to do is I'm going to call on Nate to sort of help us out. We can do this mathematically, but we're also sort of generalizing in a way. Again, no two bolts of lightning are going to be the same. One bolt of lightning might have this much power, where another might have this much power. If you're trying to travel back to the future in a DeLorean that's powered by lightning, I don't know if one bolt of lightning might work and another one might not. But let's think about a general lightning bolt. So looking up some data, let's think about a couple things first. So what we want to get to, I think to understand this correctly, is we want to think about power in terms of watts. Because if we think about power in terms of watts, we can think about how it powers our house. Let's start with just an agreement, and this is not true for all houses, but let's start with an agreement that we use about 2,000 watts of power an hour in a house. Are we cool with that, Nate?
2,000 watts of power per hour?
Yeah.
All right.
Which would mean that we use how many watts of power in a day? How could we figure that out?
2,000 watts per hour. Mm-hmm. I'm going to put watts per hour. And we have 24 hours in a day. Mm-hmm. So, in order to figure that out, we would just grab one of these calculators and do 2,000 times 24, and we get 48,000 watts per day.
And again, big generalization. A lot of us are not using the same amount of electricity at night as we are during the day. So your house may use much less power for this. We're just going to pretend we're using 48,000 watts of power in a day. Okay. If we accept that, then there's some general data we can take from a lightning bolt. So lightning bolts, there's sort of two ways to think about electricity. Oh, there's more than one that. But when we talk about voltage, we're talking about sheer raw power. And then we also talk about ampage sometimes. When we're talking about ampage, we're talking about flow and how easily that power flows from one point to another. So there are ranges of power and ranges of flow depending on the lightning bolt. And the ranges that I found when I looked this up online were between 5 and 200 kilovolts. So Nate, can we just average that in the middle and say 100 kilovolts?
100
kV.
kV.
We'll just say kV for kilovolts. And then ampage tends to be between 40 and 120 kiloamps. So let's average at 80 kiloamps. Does that seem fair?
Sure. And is that Ka?
Ka, you got it. Again, voltage being power, ampage being flow. So there's a really simple equation that we use in physics or electrical engineering, which is that wattage is equal to volts times amps. So really simple equation, W equals V times A.
So wattage equals volts times amps.
Yep. So the first thing that we would do here is figure out, okay, like what kind of wattage does this lightning bolt produce? So we would multiply, and again, this is a very average lightning bolt. We picked middle numbers for voltage, middle numbers for amps. So we would need to multiply what?
To find wattage?
Yep.
Volts times amps, so that 100 times 80?
100 times 80.
All right.
All right, so we get 8,000.
8,000, yep.
Right? And so that's going to be 8,000 kilowatts.
8,000 kilowatts.
Okay, so we're gonna kick that over because they were kiloamps and kilovolts that we multiplied together.
Okay.
So if you could just, Nate, since they're kilowatts, kilo is the prefix for thousand.
Right.
So we have that 8,000. If you could just add 3 zeros to it, we'll say 8 million.
So
8,000.
I'm gonna throw 3 more zeros there. We got 8 million.
Okay, we're doing good. I'm gonna try to wrap this up quickly. So let's accept that a lightning bolt happens in about 1 second of time. So we get 8,000 volts per second.
8,000, okay.
Right? So we would need to then divide 8 million, sorry, watts, right? 8 million watt seconds by
Okay.
3,600, because that's how many seconds are in an hour.
So 8 million divided by 3,600?
And I'm moving a little fast through this just because we're getting toward the end of the show, but there's 3,600 seconds in an hour, so I'm trying to convert the watt seconds to watt hours. So what do we get, Nate?
2,222.22222.
Okay, so 2,000. So the number that Nate just said, and he's going to write it up for us, is the hourly wattage, right? And if we think about we have 24 hours in a day, we should be able to do one more division problem, right? And figure out how many hours this will last us for. Or no, sorry, we can figure out how many days this will last us for, right?
So am I dividing?
We'll divide by 48,000 amps, right? Okay, we need to wrap this up
Yeah, we gotta
because we're
wrap it
about
up.
the end of the show. I will try to finish this next time.
Yeah.
Sorry that took so long.
A lot
No
longer.
problem.